Thanks very much for the opportunity to present our work today. I'm Yali Du. The title of my presentation is a joint learning model with variational interaction for multilingual program translation. The authors are Yali Du, Hui Sun, and Ming Li. Our affiliation is with the National K Laboratory for Novel Software Technology, School of Artificial Intelligence, Nanjing University. Programs implemented in various programming languages form the foundation of software applications. To alleviate the burden of program migration and facilitate the development of software systems, automated program translation across languages has garnered significant attention. Previous approaches primarily focus on pairwise translation paradigms, learning translation between pairs of languages using bilingual parallel data. However, using pairwise translation methods faces the following limitations. First, there are cross-language data distribution shifts in the translation. In addition to syntax style shifts between different languages, the code functional distribution is also different in the corpus of one program language. Second, the parallel corpus is necessary in pairwise translation, but there are few bilingual complete samples. For example, the bilingual complete samples in cost data site only account for 12.56%. In this paper, we argue that jointly training a unified model to translate code across multiple programming languages is superior to separately training with pairwise data. A program implemented in different programming languages should exhibit the invariant language shared semantics, like perform the same tasks. Thus, joint training on multiple different implementations of a program can complement and enhance the learning of the language shared representation. By constructing the unified language shared latent space, the rich resource languages can benefit the low resource languages in the translation. Building upon the above idea, we propose an innovative approach called Variational Interaction for Multilingual Program Translation, termed VMPT. VMPT disentangles each code into language-shared features and language-specific features based on information theory. The language-shared features should be task-specific and language-invariant, like the functional semantics of the program, while the language-specific features should be language-specific and task-invariant, like the grammar or syntax of the programming language. Therefore, each code can be generated through the interplay of these features. To enforce disentanglement, there will be a new rational interaction bound for the objective, compared to the evidence lower bound in the traditional rational inference. By optimizing this new rational interaction bound, VMPT learns to generate code based on disentangled features. This enables program translation from a source language to a target language by using the language shared feature from the source language and the language-specific feature sampled from the prior distribution of the target language. The VMPT is architecture-free, which can theoretically and practically be adapted to arbitrary sequence-to-sequence architecture, which involves an encoder and a decoder. Based on the experimental performance, we finally set up a unified encoder for all the languages with sharing and an independent decoder for each programming language. So how to learn from partially missing samples? For example, this is the most extreme case where only instances of the Java language is not missing. We sample a set of procedural instances from the training dataset randomly to fill the missing instances of the corresponding language in the original sample. When the language-specific representations and the shift-shared representations are disentangled by corresponding Q5i and R5i, however, as some instances of the sample are missing, the language-shared representation cannot be inferred. To overcome this issue, the method generates the draft translation of the missing instances with the procedural instance. Each language-specific representation of the procedural instance and the language shared representation of Java instance distinguished by R5i are input into P5i to reconstruct the representations of the multilingual instances. Then there are multi-parallel samples to infer the language shared representation, and each language-specific representation of the instance and the language shared representation of Q5S are input into P5I to reconstruct the representations of the multilingual instances. Then the missing instances can be correctly generated. Especially the KL divergence between R5i and Q5is can bound the disentanglement. Therefore, the above limitations can be solved. Based on the feature disentanglement condition generation, the code of any functionality in any language can be extended during the training process, and WinPT directly models the joint probability of multiple languages. In experiment, we conduct experiments on the public course dataset, which is a large and comprehensive dataset to evaluate the performance of program translation approaches. The dataset consists of both NIF-level and program-level parallel data from 7 programming languages, including C, C#, C++, Java, JavaScript, PHP, and Python, and up to 42 programming language pairs. The first research question is what is the performance of WinPT comparing with baseline approaches? The answer is compared with the pairwise approach, the multilingual approaches perform significantly outperformance. We can attribute these results to first, the expansion of the representation scope as the different language corpora faces various application scenarios and have different functional preferences. Second, the better lattice space, which can be jointly constructed by different languages to represent the language sharing semantics. And third, the auxiliary benefit to low resource language with rich resource language. The second research question is what is the impact of variational interaction for the WinPT? We set a blank controller which ablates variational interaction on WinPT. Across most pairs, WinPT achieves higher performance than the blank controller without variational interaction, indicating that variational interaction indeed enhances translation quality. The third research question is which rich resource languages benefit the low resource languages? With the auxiliary of any other programming languages, the performance of each direction of program translation has obtained a significant improvement. The imbalance of the data of different auxiliary languages compared or interpreted programming languages, syntax similarity influence the auxiliary ability. The last research question is what is the development complexity of the joint model and pairwise approaches? To compare the development complexity between the pairwise approach and WinPT, we record the space overhead of the translation model. With the number of languages in translation increasing, the number of parameters of the pairwise approaches grows exponentially and WinPT grows linearly. When the multilingual translation gradually increases to 7 languages, the pairwise approach should construct 42 encoder-decoder models for the 42 directions in translation. In this case, WinPT only need 1 weight sharing encoder and 7 decoders, where the number of parameters is less than 1/15 of the pairwise approaches. It demonstrates the space efficiency of multilingual program translation. In conclusion, we argue that jointly learning a unified model to translate code across multiple programming languages is superior to separately learning from bilingual parallel data. We propose variational interaction for multilingual program translation. With the variational interaction, WinPT achieves significant improvement in multilingual program translation, means and leverage the capability of non-parallel data, addresses the distribution shifts of program semantics across languages, and serve as a unified model, reducing development complexity. In the future, more effective selection strategies in fitting the partially missing samples can be explored beyond the random selection used in our method. Our replication package is publicly available. Please feel free to contact me if you have any questions. That's all. Thank you very much.